So let's review where we were last time. I've drawn a diagram up here. So you recall that we talked about a couple experiments where there were two observers. One of them is moving relative to the other one. And we want to know, for example, that if the length of this rod for one observer is x or delta L prime, that what will be the length of that rod observed by another observer who's moving relative to that person. Okay? And we said that these concepts came out, this whole idea of time dilation and length contraction came out because the speed of light has to be the same for Bob and Alice, regardless of which one's holding the light source. Right? And that doesn't add up in our normal thinking. Right? Normally, if I'm traveling with velocity v1 and I'm on a train moving at velocity, how do I say this? If I'm on the ground watching a train at velocity go by at v1, and within that train there's a fly going forward by another velocity v2, then from the ground I add velocities, right? We said that. And what happens in relativity is that that principle does not hold, that velocities do not add. It's contrary. And the only way we can get around that is to say that time and distances measured by these two observers are not the same. They're not the same. Okay? So when we did this last time, we derived a couple equations, and one of them was that that as we look at this particular example of the experiment in question, Bob was emitting light from his origin to the end of a rod and reflected back again. You recall we had a mirror here, and we did some experiments and asked what did Alice see when Bob did his experiments. Now Bob is in the rest frame of the rod, so it's important to keep that distinguished concept in mind. But the result of the experiment was that Alice sees the length contraction, sees the rod contracted, and the relation between Alice's, we should say relative to Bob, and the relation then was that the length of the rod that Alice sees, which is equated right here, was equal to the length of the rod that Bob sees. So this was Bob's observation. And remember, well, we'll get this in a second. And then times the square root of 1 minus v squared over c squared. Okay? And that is the notion of length contraction. Bob's frame of reference, by the way, is the reference in which the rod is stationary, and we call this length the proper length. So in the rest frame, delta, which is delta L prime is called the proper length. So the proper length is the one in which the object is at rest. Right? And this is, of course, what we call length contraction. And similarly, the time between two events gets dilated or increased for Alice relative to Bob. Okay. And so we expressed that this time difference between two events was given by delta t is equal to delta t prime divided by the square root of 1 minus v squared over c squared. And since delta t prime is the time in the rest frame of the apparatus, we call this the proper time. In the rest frame of apparatus. So, it's important to keep this in mind. Who's in the rest frame? That's what's going to determine whose time gets dilated and whose length gets contracted. Bob is in the rest frame with respect to his equipment. Alice is looking at at Bob moving by her. So this were the equations that we had last time, right? That this was the equation for a length contraction, and this is the equation for time dilation. Oh, and of course, inferred from all this, that c is a constant of nature, which is 3 times 10 to the 8th meters per second. Right? And what else do we have? That's about it. I am going to introduce a couple new abbreviations. One is called gamma. Gamma is the Lorentz factor. It is given by 1 minus v squared over c squared. And sometimes we'll use beta, which is equal to v over c. So these are two abbreviations that are often used because these terms come up so often that we need some abbreviations for them. Now, one thing to keep in mind is that, and you'll notice this here, that v must be less than c. Okay. For any real objects that exist in nature, in this case, Bob and his rod, Bob and his rod, this velocity v can never be greater than c. It has to be less than c. Why? Because if v is greater than c, the square root becomes imaginary. Right? So times have to be real, lengths have to be real. So velocity of any object relative to any other object can never be greater than c, the speed of light. And only one type of phenomena can travel at the speed of light, and that's light itself. Everything else travels slower. Okay? So that's one corollary right here. The other thing to keep in mind is that this, we could call this the dilation or the contraction factor. That gamma is, so beta is always less than 1. And that means that gamma is always greater than or equal to 1. Okay? So gamma is always greater than 1, and beta is always less than 1. The velocity relative to the speed of light. Okay, so if there are no questions on that, if there are, raise your hand. Or forever hold your silence, or at least until the next time I ask the question. Okay, so yeah, it is good to try to do a couple of problems. We're going to do a couple problems involving rockets traveling to nearby star systems. It's a way of exemplifying how this time dilation works and getting a feel for it. So we've got an example where we have, let's say, Bob, who is our guy that's traveling over here, and he's in a rocket ship. So Bob travels. This is not a good pen. Thought we had another black pen. can. So Bob travels from Earth to nearby to a star that is 4.2, 4.3 light years from Earth. Okay, and we want to know how long does it take Bob to reach the star? How long does it take Bob to reach the star? Okay. Now, there's a couple ways we can work this. First of all, we need to clarify what the length light year means, and so a light year is the distance that light travels in 1 year, right? So, for example, if I want to have, for example, 10 light years, then my abbreviation here, 10 light years would be equal to c, the speed of light, expressed in meters per year, times 10 years. Okay. So light year is c times the number of years. Okay. So that's a way of expressing what the actual distance of light years is. So and we will say star, and we must say according to Bob. So remember, obviously, it depends on who's doing the time calculation, according to Bob. Okay. So there's a couple ways. In which we can work this problem. One of them is that we can do is to say. Well, let me preface this by saying something that's very important. When you do a calculation for velocity, okay, everybody can calculate velocity. Velocity is equal to distance divided by time in your own frame. So Bob can calculate velocity and Alice can calculate velocity, and they can both use the formula to calculate it the same way. Okay. So one way we can do this is to say that if we look at now, I probably need to draw this out in a little bit more detail. Let's do it this way. Well, almost there. So here's Earth. And here is star X, right? The star. And we know that in the Earth system, that the distance from Earth to the star is 4.3 light years. That's the distance. Alice stays on Earth. Bob takes off in his rocket ship, and he is traveling at a speed of 0.8 c times 0.8 times the speed of light. Okay, and we want to find out how long it takes for him to reach the star. Well, first of all, I know I can calculate this based on what Alice says. Alice is watching this object move from Earth to the star. In her frame, we know that the distance is 4.3 light years, and it's traveling at this speed. So the time that, based on Earth, so delta t Earth is going to be equal to the distance, 4.3 light years, so 4.3, and now I'll put c times the number of years, c years, so c is the number of meters per year, times the number of years, and I'm going to divide that by the velocity. So v is the velocity, and that's 0.8 c. And the c's cancel. Notice that c here is a c to here, it cancels. So if I take 4.3 divided by 0.8, I get 5.37 years. So far, there's nothing unusual about that. If I told you you were traveling at a certain speed and you had a certain distance, then you could calculate the time, right? Okay. But now we know that things look a little bit different in Bob's system because Bob is now, imagine that there's a rod or going from Earth out to here, out to the star, then he sees this rod, this distance being contracted. Okay? So Bob is going to say that the distance to the star is equal to 4.3 light years times the square root of 1 minus v squared over c squared. And since v is equal to 0.8, I do the math on this, and this becomes 4.3 light years times the square root of 1 minus v squared over c squared, and that looks like about 0.6, I believe. So so the length that he is going to see that he has to traverse is 4.3 times 0.6. Anybody have a calculator? 2.58. Thank you. Okay. So he says, oh, I only have to travel 2.58 light years, and not only that, but this star, I'm sitting now on this rocket, I see the star moving towards me at a velocity of 0.8 c the other way, right? If I'm riding a train, that thing's coming towards me. So how long is it going to take me to reach this star? Well, I'm going to calculate the Bob's time. Which we'll call delta t prime. Okay. And that's going to be equal to the distance that he thinks he has to travel, which is 2.58 light years. So we'll call it c times years is the distance. And he sees the star coming at him at a speed of 0.8 times c. And so he comes up and he gets the time that he calculates is 3.27 years. So basically what we've just shown is that Bob says that he's going to get to the star in 3.25 years, and the Earth-based system says it takes Bob 5 and a little over 5 1/3 years. Right? Almost 2 years difference in time. Now there's another. We'll come back to the meaning of that in a few minutes. But another way we can approach the problem. Another way that we can approach the problem is to say that if we've just calculated the Earth time, so this is delta t measured on the Earth, then I can use the formula that says that the delta t of the Earth, or the delta t for Bob, which is writing on the delta t prime for Bob, is equal to delta t of the Earth, which is the time that the Earth says, that the Earth-based person says that the trip took. And now I want to multiply this by the square root of 1 minus v squared over c squared, and this will give me another way of calculating Bob's time for the trip. So I get 5.37 years is the Earth time, times the contraction factor, which is a square root of 1 minus v squared over c squared. And we just calculated that somewhere, I think it was 0.6. And so we should get the same answer of 3.27 years. Okay, 3.27 years. So two different ways we can calculate it. We can either look at this and say, Bob's moving very fast, so he sees the distance to the star shrink, and therefore he's going to get there sooner by his clock. That's one way of looking at it. You just take that shrunken distance and divide by the speed at which the star is approaching him. Or we can do is calculate the time that the Earth-based observer says that it takes to get there, which is 5.37 years, and then apply the contraction factor to find out how much time it took in Bob's system. So, a lot of questions I guess we could ask about this. If Bob's going to the star, okay, so now the question is, if he's planning a trip to get to the star, does he need to have 3¼ years of fuel supply, food, and oxygen, or does he need 5.5 years of food, oxygen, and fuel? Yeah.
Is this a one-way trip?
Right now it's a one-way trip. Well, it will be if he runs out of fuel. No, we're going to actually look at a round trip in a second. Okay. So right now, basically, let's assume it's a one-way trip. Yeah, and he's going to go there, and he'll have a rescue mission that brings him fuel to come back at a later time, right? But the question is, to get there, does he need 3 1/4 years of fuel, oxygen, and food, or does he need 5.37? Because according to the Earth-based person, she sees him gone for 5 and 3.37 years. Bob's the only one that has to worry about whether he gets there. His fate is really tied to that. And for him, it only takes 3 1/4 years. So that's all he needs to get there. What Alice, or the Earth person, is going to say is that he's breathing more slowly. His fuel consumption is less than, the rate of fuel consumption is slower. He's eating fewer calories per hour, and therefore she's going to say, yeah, that's the way it works, because in his time, he's going to get there in 3 1/4 hours, or 3 1/4 years. I'm sorry, 3 1/4 years. Right? Okay, so the answer is you only need this. Now, let's suppose next that Bob turns around and he comes back home, and we want to ask the question, which is that if Bob left in the year 2019, and of course we could say January 2019, when he comes back, what year will it be when he comes back, according to his clock? Well, it's going to be this number times 2, right? I'm going to multiply this number times 2, because it's going to take him 3¼ years to go out and 3¼ years to come back. So, what's that?
Summer 2025.
Summer, right. So Bob, on return, it is, we'll call it June, you call it summer, we'll call it July 2025, right? Now,
So he saved himself 4 years?
I'm sorry?
He's going to be 4 years younger.
He's going to be 4 years younger. Right, right. So what's Alice going to do? What is Alice stayed behind and her friends, right? What year is it in her frame when Bob gets back?
29.
29, right? So now we take this times 2. This becomes 10.7 roughly, right? 10.7 years. So now I add that, and this becomes 2029, and it's somewhere in August, we'll say August or July 2029, and lo and behold, Bob is 4 years has experience is 4 years younger, then will have aged 4 years less than his friends remaining on Earth. Okay. And that is the way relativity works. Now, will he have experienced a difference in aging? Either one? No. Everyone individually still feels they have lived a normal time span. Bob will feel, and he actually is, 6.5 years older when he returns. 10.5 years. Okay? So this brings up the interesting concept that you have a homework problem on. What if they were identical twins and one of them went out, and let's suppose that they came back and now Bob was 40 years younger than his twin sister, Alice, right? Then he would see her as an old lady when he got back, and he would still be relatively young. And those of you that may have seen, there was a movie by Matthew McConaughey called Interstellar, if you haven't seen it. And at the very end, you see he comes back after going through a similar experience, and his daughter he's like 50 and his daughter is 80. And he's able to talk to his daughter right before she dies. And so they actually used a Caltech team to add the science part of the science fiction to the story. But yeah, okay, now we're ready for questions. Yes?
So if Bob theoretically brought a clock on his trip,
Yeah.
would the clock be the same like moving time on his spaceship than on Earth?
He would see it look like it is the same, right? For him, an hour of the clock still feels like the same as what Alice experiences as an hour, or as he would experience it if he was there with Alice for an hour.
So would it be going faster?
Would it be going faster?
The clock would be going faster?
So so let's look at it this way. When Alice looks at Bob's clock is going slower. In other words, more time passes for her than for Bob. That's time dilation. Right? That's this statement right here. The time between two events gets dilated for Alice relative to Bob. So she doesn't. Yeah, that's. Go ahead. Yeah.
So does this happen in like nanoseconds for if I got on an airplane and flew to halfway across the world?
Yes, yes. And there was an experiment done in the 70s where they took an atomic clock and they flew it with in-flight refueling, and they circled the globe, and they did it one way and then they did it the other way, and they actually observed the time dilation. The difference was I believe about a microsecond. I'd have to look it up again, because what happens is that if V is very, very small, this becomes imperceptibly different for the two observers. And by small, I mean like millions of miles per hour. That's what I call a small velocity, right? you have to literally be going at light speed or something close to actually get large numbers where the difference is significant. Right? So you have to be going at like 10%, 20%, 80% the speed of light before you get into ones that are, which would be more obvious to us. Okay? But we can say this, that there's a problem like this in your homework. If you have a neutron, which normally, if it leaves the nucleus, it's unstable and it decays. And the neutron decays into a proton and electron, and with another, proton plus an electron plus another particle we call a neutrino. And it's also massless, and it does also actually travels at the speed of light also. But the point is that this process in the lab takes of the order of 15 minutes. 15 minutes is what we call the half-life, T1 half. So the decay time for a neutron in the lab sitting here, once it leaves the nucleus, will be on average 15 minutes. Now I take that same atom and I boost it to the speed of light, or let's say we boost it to the speed where gamma is equal to 2. We'll do another example of this later, but that's roughly of a velocity of about 0.86 times the speed of light. And then what we find is that the lifetime of the neutron is now 30 minutes. And that's a measurable effect. Right? That's a measurable effect. People have observed that if the atom is, and that's the nice thing, of course, about atoms, is that unlike humans, we can make them go at the speed of light. Right? Or we can make them go close to the speed of light. So this is a real effect. This time dilation is real, and it can be measured with a macroscopic time for subatomic particles. Okay. Okay. So yeah, go back. Yeah.
Just real quick, that 0.6, that was your multiplying the 4.3 light years back.
Yes.
Where did that come from again?
Okay, so V is 0.8 times C. So if I put, that means that V over C is equal to 0.8, right? So if I put that in here, then I get that the square root of 1 minus 0.8 squared is 0.6.
Oh,
And you, yeah. Yeah, that's kind of an interesting problem. Okay. Any other question on this before we go on? It's going to take a while for it to sink in. The important thing to realize is that, or to think about, is that if you are in the rest frame of the apparatus, of the event, then your time is always the shortest, and your lengths are always the longest. Anyone moving past you, okay, is going to see shorter lengths and longer time between two events. So that's why it's important how you distinguish which one you're looking at, who's in the rest frame of the apparatus. Right? So in this case, Bob is in the rest frame of his apparatus. Bob is in the spaceship, and he's got a clock, and that clock is at rest with respect to Bob. Right? The clock is not at rest with respect to Alice. Right? So Bob is in the rest frame, so his time is always the shortest. Okay, so I know it really takes a while for this to sink in. That's why. Have any of you started the homework problems? Looked at them yet? Have you looked to see whether they're available? Does anyone knows that? Yes, they are available. Okay, good. Okay, so let's look at another one real quick. Not real quick. Nothing's quick with this because it's
Unless you're in the rest frame.
What's that?
Unless you're in the rest frame.
Unless you're in the rest frame, right? That's right. Okay, so now we got another one. Let's say that Bob is also in the moving frame. So Bob is still the mover, right? He's the one moving with respect to the ground. Alice, we said, is in the earth frame. So Alice is back here. And by the way, we call these frames S and S prime. And S prime is always moving to the right with respect to S. And who you call the rest frame really depends on the problem you're trying to solve. So you cannot identify one of these or the other as the rest frame. Although in this case, we've taken it to be this one because Bob is doing the experiment at rest with respect to his time. And Alice is looking at Bob. Alice is looking at Bob's experiment. Okay, so the problem that we're going to look at is, let's say that now Bob wants to get to a star 20 light years from Earth. And he wants to do it in 4 years. Okay. How fast must he travel? How fast must he travel? Okay, well, first of all, we know that in the Earth frame, this is not possible, right? Because even if he was going at the speed of light, it would take him 20 years to get there, right? He can't do it before. So the only way he's going to be able to do it before is to contract his distance, right? So the first solution is Bob is going to have to figure out his contracted distance. So what he's going to do is to say, okay, the Earth-based distance of 20 light years, Earth-based distance 20 light years, has to get contracted by a certain amount, which is dependent on my speed. And now I'm going to use the parameter beta instead of v over c because we just made that our new definition that beta is equal to v over c. Right? So beta is always the velocity, it's the percentage of the speed. It's the velocity as a percentage of the speed of light, or as a fraction. Right? So this is his contracted distance, and now he needs to divide by his own speed to get his time. So his time will be, so delta t prime, which is Bob's time, is going to be 20 light years times square root of 1 minus beta squared, divided by beta times c. So in other words, Bob is calculating his time as distance divided by speed. So this is distance divided by speed. Okay? That's Bob's time. That's what he's looking at. Now remember that a light year, we can replace light years with c times years. So this is actually c times the years. And we know that he wants to be able to do this in 4 years. Right? So we want this, what is the value of beta so that the time for him to make this trip is 4 years? Right? Well, now it's solved. Right? I mean, this is an equation solving for beta. Right? So that's how I get the answer. Right? So now what I do is say, well, c cancels out, so I have the c that cancels out the c. Now I square both sides, and I get 400 times 1 minus beta squared equals 16 times beta squared. And I solve for beta, and I get that beta is equal to 0.98. Okay? So if he wants to get to a star 20 light years away, and he wants to be able to get there in 4 years, he has to travel at 98% the speed of light. Right? And now, how much fuel, how much oxygen, how much food does he need? He only needs 4 years worth to get there. 4 years there and 4 years back. Right? But, and this is a big but, he better not slow down. Okay? Because if he slows down, then suddenly this distance to the star zooms way out again. And now he's not going to have enough fuel to get there. Okay? So he cannot slow down. Or he'll run out of food, he'll run out of oxygen, and he'll run out of fuel. Right? Because going slower is worse for you. It's making your trip longer. And not just in the way of, like a normal slower velocity makes you take you longer. It's because your distances is also getting longer to get there. Okay, so we got this, right? This is, these are basically the two different types of problems that you have for calculating this type of a thing. This getting familiarity with time dilation and length contraction. Okay, any questions? Take a minute. You can take a minute.
We don't have to calculate how long it'll take him to get to the speed of light ever, will we?
No, we're not going to. So in all of these problems, and this is the way it's often, explained, is that you can make the trip long enough. Now there are cases where you have to do that. But if you imagine that you make the trip long enough so that the acceleration time is small compared to the constant velocity time, then this approximation works pretty close. So we are neglecting acceleration. We are neglecting acceleration. And that's part of the general theory of relativity, which one can also do, but it's more complicated. There's whole courses, graduate courses, that just deal with a whole course on general relativity. That's what I do. Any questions on this? Okay, good. Okay, so now what I want to talk about is what we call the general coordinate transformation. And up till now, we have basically done problems where the events in Bob's frame always take place at the origin. He sends out a light beam at the origin, it reflects back, and he detects it at the origin. So we're always looking at the time difference of two events at a fixed point. Right? He emits it from this point, and he receives the light at this point. Right? In his frame, both events occur at the same location. The emission of light and the reception of light. Now, in general, that's not going to be true. For example, supposing Bob has a laser gun and he's trying to hit a target over here. Now I want to know, for example, that if it takes a certain time for the bullet to leave, or the light gun to leave his gun and arrive at the target, now I need to calculate that for Alice, and the answer is going to be different, okay? Because the two events are located at two different locations, right? Up till now, it's only been one location. So the general question, I guess I can erase this now, as soon as I put these colors back on. I will write out the general equations or problems that we are looking at. But I'm going to try to keep that picture of the two events up there. So here's our general question, and we can ask it two ways. We'll look at it this way. Suppose an event occurs. Another bad pen. Sorry. Good pens are hard to find. Suppose that we have an event that occurs in Alice's frame, and it occurs at a position we'll call it x sub a on the x-axis, and it occurs at a time t sub a on the x-axis. Time t sub a on the x-axis. then I can identify a space-time coordinate for this event at this location at this time. Right? In other words, for example, a person, Ken is standing right here, he switches on the light. That's an event. It occurs at a certain time and at a certain location. Or Mary starts jumping up off the ground, right? There's a certain time at which she leaves the surface. That's an event. Or Bob fires a gun. Right? There's a certain time that the bullet leaves the nozzle. Right? Those are what we call events. And they occur at a given location, and they occur at a given time. So the question is, if I have a certain event occurring in Alice's frame, at which XA prime, TA prime, does this occur? In Bob's frame. Okay? That's the general question that we're trying to answer. So we have a certain XA, TA here, and then for Alice, where does that occur, and what time did that occur for Bob? And it can be anywhere. By the way, just to keep things simple, and because they really are this simple, that what we find out in relativity, fortunately, is that if it occurs at, for example, a y coordinate, y sub a, because this is a one-dimensional point in space, then it turns out that the y coordinate is the same for both Alice and Bob, and the z coordinate is the same for Alice and Bob. So just like in non-relativity, I'm sorry, did I say this right? YA equals, it made a mistake, YA prime, and ZA equals ZA prime, and this is for event A. A is the event. Okay? It occurs at a certain point, X sub A, at a time T sub A. And we want to know that, which is measured by Alice, and we want to know where did Bob say it occurred and when did he say it occurred. Okay? Now in the old system, we would just say, well, TA prime equals TA. The old system is, yeah, okay, it was the same time. Time is universal. But we now know that this is not the case. Okay? So there's a transformation, there's an equation that's going to relate the two. Now we're not going to derive it, but I am going to state how to answer this problem. And the answer is that the way that Bob needs to calculate this is the equation for the transformation is that this occurs at XA prime equal to gamma times XA minus VT sub A. Okay? And it occurs at a time, T sub A prime, in his system, that is given by gamma times T sub A minus V over C squared times X sub A. Right? So what this tells me is a formula that says if I know where and when the event occurred in Alice's frame, I know XA and TA, then I know how to calculate where and when it occurred for Bob. Right now for us it's just a formula. Now the derivation of the formula is a derivation that's not in your book. It is in Giancoli, but it's based on the following assessment or assumption. We always start with a case where as the coordinates are moving by each other, that there is a point in time where at t equals t prime equals 0, x equals x prime equals 0. In other words, initially, if we define the time t equals 0 to be the one where Bob's x-axis crosses with Alice's x-axis. That's the initial condition. And we assume that before, and we assume that still. So these conditions are implicit. Now, the derivation basically is basically the same idea that I have a light wave that is propagating away from Alice that occurs not only in Bob's frame, but it occurs for Alice. And it really doesn't matter who emitted the light frame, the light pulse, because they're traveling the same speed in both frames. So the derivation is based on this concept of relating the two by using the fact that I have a light beam that's expanding out from the origin, a light beam expanding out, and I'm going to be able to relate these two coordinates together. Now, we're not going to do that. We're going to give you the answer, and the answer is stated right here. And maybe there's some wisdom in that. Maybe, in fact, you actually learn better by using the equation than deriving it. But if you want to see the derivation, it's in Giancoli, and Giancoli's book is in the Math Physics Library on Reserve. That I'll leave up to you. Okay. Now, that's one thing to keep in mind. The other thing to keep in mind is that this answers the question at which, XA prime, TA prime, does this occur in Bob's frame? But I could equally well take the other point of view and say, what if I know the coordinates that an event occurred, and we'll call it another, I guess, well, should we use the same one? Yeah, no, we'll use the same one. That this event A occurred at XA prime, TA prime in Bob's frame, and I now ask the inverse question. At which XA TA did this occur in Alice's frame? Okay? So it's the inverse question. In this case, I know that there was an event, and Bob observed an event at a particular location at a particular time, and that is a coordinate which we define right here, XA prime, TA prime. And now I want to find out where and what time did Alice say the event occurred. So the inverse is basically the same as this, except I reverse the prime with the non-prime, and I change the minus to a plus. Because if I'm in Bob's frame, he sees Alice moving in the direction minus V, right? Bob's in minus V. So you know that by symmetry that I'm going to be able to have something that's going to look like XA prime plus VTA prime is going to be equal to XA equal to XA. And I've just changed the plus V or minus V to a plus V, because now it is Bob looking at Alice, and I changed the prime coordinates to the n prime and the n prime to the prime. Similarly for TA, I'm going to do the same thing. I'm going to change the prime coordinates to the n prime coordinates, and it's going to be gamma times TA prime plus V over C squared times X sub A prime. Okay? So these two go together when I'm trying to go from Alice's event coordinate to Bob's, and these two go together when I'm trying to, or maybe if I need to rewrite it down here, X sub A equal to gamma, I'll just rewrite it here, so they're all together, XA prime plus VTA prime, right? And these two go together, okay? Here I'm converting Bob's coordinate to Alice's, and here I'm converting Alice's coordinates to Bob's. Any question? We're going to go through an example of how to use it, and then hopefully it'll be a little a little clearer. But basically, this is a transfer. You understand the question, and you understand how to get the answer. Right now, that's all we're looking at. You know, there was an event that occurred with a certain location, time, analysis frame. When and where did Bob say that event occurred? In his coordinate system. That's all we're doing. Subject to the initial condition that at t equals t prime equals 0, x equals x prime equals 0. Okay, are we good? Okay, good. All right, so let me see if I should, I'd probably like to use a new board, but I mean, this one's not so hard to erase. So now we get to actually this is an interesting question. I think that you might actually enjoy thinking about this. If you really like puzzlers, if you really like what do you call it? Mind twisters, right? This is definitely a mind twister, a paradox. So the story goes something like this. Alice and Bob are talking about the theory of relativity, and Alice comes up with an experiment. She says, I've got a, would it be better to use this board because of the background, Pasha? No? Think it matters?
Still good, either one.
Okay. So basically, Alice says, I've got this idea. She says, suppose I want to ask the question, can a 10-meter rod, I'm sorry, I made that up, 20 meters. Can a 20-meter rod fit inside a 10-meter barn? Right? Well, now we sort of think we know the answer, because what I'm going to tell you next is probably sort of obvious based on that. If I now take that rod and I start moving it very, very fast, it's going to shrink. Right? It's going to shrink. It's going to shrink by this factor that we just derived last time, what we call the Lorentz factor. So Alice says, I think what we can do is, let me draw a picture here. I've got a coordinate system, and of course this coordinate system is for Alice. And she's got a barn that's 10 meters. That's 10 meters. 10 meters long. And her hypothesis is that if she takes a rod that is 20 meters long in the rest frame, so we'll say that, in this case, we'll say that, well, if you are riding on the rod at the speed of the rod, and that the length of the rod is 20 meters, right? That sure enough, in Alice's frame, we would expect that delta L is equal to delta L prime times the square root of 1 minus v squared over c squared. Now, we will take a velocity such that, for example, in this case, that v over c is equal to 0.87, and therefore the square root of 1 minus v squared over c squared is equal to 1/2. Okay? So we know that by moving it very quickly, the rod is going to collapse, it's going to shrink, and now you can see that I get a length delta L of the rod. According to Alice, this is by Alice's measurement, right, is equal to 20 meters by Bob's measurement times 1/2. And that, in fact, is equal to 10. And 10 meters is the length of her barn. So she says the rod fits. I can accelerate the rod to whatever this number was, 0.87 times the speed of light, and the 20-meter barn, the 20-meter long rod will shrink in Alice's. So this is Bob, who's writing up here, and this is Alice, and she's down here. right? And Alice is in the unprimed frame, so we call this X and Y. And the length, this distance here is, of course, 10 meters. Right? And she does the experiment, okay? So her experiment is, she has a light sensor on both sides of these barns. And what she observes is, by the length contraction, is that when the right end of the rod reaches the right end of the barn, a light goes off, and when the left end of the rod reaches the left end of the barn, a light goes off. And she makes what's called a coincidence signal, which is, says, if these two events happen at the same time, the rod fits. And she has a coincidence unit, which basically says, when this guy got inside, when this right end of the rod reached the right end of the barn, I sent a signal to my logic unit, and when the left end got inside the left end of the barn, I sent a signal to my logic unit, and if they occurred at the same time, then I get a pulse out, and it's in. She does the experiment. Bob says, no, that's not what's going to happen. That's not what happens at all. Here's the problem. If I'm Bob and I'm writing on here, then Bob says, look, I'm writing on this. My rod is not getting shorter. Your barn is getting shrinking. Right? So this is all from, we'll say, Alice's point of view. And now if we look at it from Bob's point of view, then what Bob sees is something else. He sees, which you'll see in his system, this is what we call the S prime system. What he will see is that the barn actually becomes very narrow. So the length of the barn has shrunk by the same factor, so it's 5 meters. Okay? And this is, in fact, 20 meters is the length of the rod, and it's not going to fit at all. It says there's no way this thing can fit. In other words, they both look at each other and they see the other person's distances shrink. And the question is, who's right? Okay? Because, Alice can look at Bob's equipment, and Bob can look at Alice's barn, and they basically, they see two different pictures of what happened. This is what it looks like in Alice's view. This is what it looks like in Bob's view. So what happens here? What's the upshot? Well, to understand it, we've got to actually go through and see which one's right. How do we calculate whether or not these two things occurred the way Alice saw it, or is it going to occur the way Bob sees it? So let's look at Alice's point of view. From Alice's point of view, we agree that at this point in time, this is the point where the coordinates overlap. Right? So at this particular point in time, we have t equals t prime equals 0, and x equals x prime equals 0. Right? This is where they overlap. This is my start time. They can agree on one coincident time between the two, and that's at the origin, or at some point. Right? So what is the time for this event occurring in Alice's frame? We will call T sub b, which is when the right end of the rod reaches the right end of the barn. And this side we will call T sub a. This is when the right end of the rod fits into the left end of the rod fits into the left end of the barn. And that is the event T sub a. This occurs at x sub a equal to 0. This occurs at x sub b equal to 10 meters. Okay. So in her frame, the left end, the right end of the barn is at 10 meters from the origin. Okay. So that's the basic concept. Now all we need, well, one of the things we need to know is what is, and we know because of this coincidence that T sub A is equal to T sub B, because in fact the rod does shrink, it fits inside the barn, but the time it takes is going to be given by the length of the barn, or the meters, or the rod, which in her frame is 10 meters, and it travels, the right end of the rod travels 10 meters in a time that's equal to the distance divided by its speed, which is 0.866 times c. Okay? So that is the time at which this occurs. All right. Now, what does Bob see? Remember, the whole point of this transformation is when Alice measures an event at a given location at a given time in her frame, when and where does Bob, that's it, right? Where and when does Bob see that event occurring in his frame? Well, so now I do is I just have to apply the same transformation equations, and let's calculate what, in fact, TA and TA and X, what the different parameters are. So what we really want to know is what is TB prime and what is T sub A prime? And are they equal? Because if they're equal, then they're coincident, and then we have a real contradiction, right? Because clearly the 20-meter rod cannot fit inside the 5-meter barn. So we do the calculation, and what we can say is that if I do, let's say, for example, let's do TA prime first. This is equal to gamma times T sub A minus X sub A times V over C squared. Right. Now, we know that the left end of the barn is at XA equals 0, so this is equal to 0. And we know also that the time that it took in Alice's frame for the rod to reach the other end of the barn was equal to 10 meters divided by 0.8 divided by 0.866 times c. Okay? And we know that gamma is equal to gamma is equal to 2. So gamma is equal to 1 over the square root of 1 minus v squared over c squared, and that's equal to 2 because we know this part is equal to 1/2. So this is equal to 2 times 10 divided by 0.866 times c, and this turns out to be, you just plug in the numbers, and for TA prime this is equal to 7.7 times 10 to the minus 8 seconds, or about 77 nanoseconds. Okay. What about, that's the time it took for the left end, this TA prime, for the left end of the rod to reach the left end of the barn. What about the other side? The other end, which is the right side, is TB prime, and I apply the same thing again. So I do gamma times T sub B minus X sub B times V over C squared. Okay. Now I know what everything is, right? I know what T sub B is, so this is equal to 2. This is 10 meters divided by 0.866 times C, and this is minus X sub B, but X sub B is in this case is equal to 10 meters, because that's the length of the barn in Alice's frame of reference, times the velocity, which is 0.866 times c, divided by c squared, and I evaluate this, and I get that this number is equal to 1.96 times 10 to the minus 8 seconds. Right? So this is 0.866 times 10 to the minus 8 seconds. So what has actually happened is that in Bob's frame, this point right here, this event is what we call XB prime, TB prime, and it occurs before TB prime. Because TA prime. Because TA prime is greater than TB prime. So he says, no, what happened was that first this right end of the rod went in the barn, and then sometime later, what happened was that in his frame, no reference, the right end of the barn passed through. So here is X sub B prime, here is X sub A prime, T sub A prime. And he says, you know what, you cheated. Yes, both lights did go off when each end of the rod got into the barn, but they didn't happen simultaneously. And she says, yes, it did. I have a coincidence unit. This end got in at the same time as this one. I have a coincidence unit. It went off. They went off at the same time. It fit inside the barn. He says, no, that's not what happened. What happened is this end of the rod went in first, then the rest of it traveled through until the other end of the rod went in, and then that light went off. And he said, well, who's right? And the answer is they are both correct. In Alice's frame, the two events happen simultaneously, and the rod fits inside the barn. In Bob's frame, it doesn't happen that way at all. First, the left end of the rod gets in the left end of the barn, but the stick is too large. The rod is too large, so you wait a longer time until the other end fits in the barn. And they both agree that that's what's happening in their own frame, individually. But they see it completely different. One of them says they both happen at the same time. The other one says no. First of all, this end fit in the barn, and then this end fit in the barn, because your barn is what shrunk, not the rod. Okay? And they are both correct. They are both correct. They just disagree on what we call simultaneity. They disagree that, now you might say, well, suppose this was hooked up to a bomb. You know, in Bob's frame, bomb doesn't go off, right? Because the events happen, the coincidence never happens. Well, it only has to happen in one frame for it to actually go off. So in fact, what Bob will say is, okay, I see why it is coincidence, because if I apply the transformation equations, I will calculate that they were simultaneous in your frame of reference. I acknowledge that, but they are not simultaneous in my frame. And the reason is that you just apply the transformation equation, and simultaneous here in for Alice is not simultaneous. And that's the only way you can explain the fact that they both see each other's distances getting shrunk. Otherwise, that would be a contradiction. Right? If it was simultaneously involved, somebody's lying. You know, the rod cannot be short compared to the barn, and the barn cannot be short compared to the rod for both people. One of those has to be wrong. Unless simultaneous in one event, in one frame, is not simultaneous in the other. Right? Because Alice sees it different. She sees this event's happening simultaneously, and the rod fits. Bob says no. First this one went in, then the rod travels the rest of the distance, and the other side went in. And that's how you resolve the conflict. Now, it turns out that GPS units, which we'll talk about on Thursday, use this transformation equation to calculate the position of where you are in your car or your home or your habitat. And if they don't use this relativity correction factor, you cannot do turn-by-turn navigation. Every GPS unit has to have a relativity correction for calculating. Otherwise, these satellites that are emitting signals, they're moving over the Earth, right? They're in motion. So simultaneous emission of light from those two satellites, or whatever time they're recording, is not the same time that is going to be acknowledged on the ground when that signal gets there. So we'll have a problem on that on Thursday, and we'll talk about that. And meanwhile, you can keep going.